Okay, good. So we can get started. So yeah. So what we'll talk about right now. So once we set out on the general theory of Poisson boundary for groups acting on spaces, and we have this sublinear tracking criterion and so forth. So then we can apply it to some more concrete situation. And I mean, the general situation is the situation of a group which acts on a hyperbolic space. So in fact, I call this a weakly hyperbolic group. So I'll give you a more precise definition. That this is a lot of this, what I'm talking about today is in this paper that I have with Joseph Meyer. So it's a general setup, so we can start generally. So what is the, so first of all, we want to define a Gromov hyperbolic space. So first of all, we say a geodesic metric space. So geodesic means that every 2 points have a geodesic connecting them. So let's call it, always will denote by XD, is called delta hyperbolic. If there exists some delta such that for every tripole point x, y, and z, you have the following situation. You have x, y, and z, and you draw the geodesics forming this triangle. So you have the geodesic from x to y, the geodesic from y to z, and then you have the geodesic from x to z. And so the space is hyperbolic if the triangle looks like this. This we call the thin triangle. So it looks like a tripod in a way. So looks like this. So how do we make it precise? Well, we say that this delta, which is uniform for all points in the space, you want that the geodesic from x to y, or any geodesic from x to z, because there could be more than one geodesic from x to z, is contained in a delta neighborhood of, the union. So of a geodesic from x to y, union a delta neighborhood of a geodesic from y to z. This is the classical picture. Very, very important in geometric group theory, that if basically the geodesic from x to z first fellow travels the geodesic from x to y up to a certain point, and then in the middle there's this delta fudge. You don't know what's happening, but only for sort of distance delta, and then it fellow travels the geodesic from y to z. So strictly speaking, that the neighborhood of geodesic from x to y is something like this, and the neighborhood of the geodesic from y to z, something like that. And so you want that this path here first is in one neighborhood, and then it's in the other one. So this is a completely metric definition, which, of course, is verified for certain spaces, but not for others. So the most famous example would be if x is a tree. So it could be an infinite tree or finite tree. So if x is a tree, basically every triangle is zero thin, because, well, for every 3 points, if you draw the geodesics, you'll get a form of tripod. You get this. So this for delta even equals 0, but in general, delta could be non. The main idea is, instead of having this idealized situation, we have a slightly more concrete coarse situation where we are allowed to make some error, but this delta is fixed once and for all. So this is a classical example. Then another classical example would be X to be H2, the Poincare disk or the hyperbolic plane. So in that case, well, if you take 3 points, well, you see that basically you only need to check. So the geodesics are, arcs of circumference, which are orthogonal to the boundary. So the geodesics look somewhat like that. Very good. And I mean, the point is that it turns out that you only have to check, as the points go to infinity, because if the points are in a complex set around, say, some base point, well, you can pick some delta. Doesn't matter if the space is finite. There's always some delta that works. And as x and y and z goes to infinity, well, they converge to the ideal situation, which is like that, where you have 3 geodesics that are orthogonal to the boundary. Okay. And well, the cool thing here is that since G, which is PSL2R, acts transitively on triples, of points, of the boundary, well, you have to check only one triangle because all such triangles have the same geometry, and so then you can measure what happens in this triangle, and then you can find a sort of incircle of this triangle, and the incircle of this triangle basically gives you the delta. And so the question is, what is delta? Well, this is a computation that you can do in this model. So if you have time, but there is such delta. So, and on the other hand, well, the obvious counterexamples are Euclidean spaces in higher dimension. So counterexample, the classical one is where X is R2 with the Euclidean metric, because in that case, you can draw a large Euclidean triangle, say equilateral, it doesn't matter too much. You can scale here. Yeah, anything you have, you can scale. So the delta that works for one triangle, since you can scale, if you get a triangle which is twice as big, you need a twice as big delta, actually. So that's another way of thinking about it. And so, of course, there is no uniform delta. So otherwise said, if this says length n, this is length n, and this is length n, well, you see that the incircle, what's the radius of the incircle? If you really care, you can, right? You can figure out what is the trigonometry. So what's going on here is what? N. So this is n over 2. This is what? N square root of 3 over 4, something like this. Is that right? Oh, okay. It's good that you're worse than me at elementary geometry. So, so this is n over 2. Okay, right? Yeah. So what? So triangle is 1, 2, square root of 3 over 2. So we divide. Okay. Over 3, I guess. right? Or square root of 3, or maybe square root of 3. No, 1, 2, square root of 3. So this is n over 2 square root of 3. Anyways, yeah. Anyways, so whatever it is, it's a constant multiple of n. So when n goes to infinity, so there is no delta. No delta independent on L. Okay, good. So what's going on? Okay, so in general, okay, so if G is a group, so G, a finitely generated group, is word hyperbolic if, well, if the Cayley graph of it is hyperbolic in this sense, which is sometimes called Gromov hyperbolic, because of course, so this theory was developed by Gromov. So if there exists some S finitely generating set, such that the Cayley graph of G with respect to S is delta hyperbolic. And what is kind of interesting here is to note that any two generating sets give rise to a different metric. But if one is delta hyperbolic, so that all the others are delta hyperbolic. So if the Cayley graph of G with respect to S is delta hyperbolic for some S, then the Cayley graph of G with respect to S prime is delta hyperbolic for any S prime with finite generating sets. And the reason for that is that the two metrics on G given by these two generating sets are quasi-isometrically equivalent to each other. So it's a little bit like this growth rate, whether the growth rate is exponential or not. Well, up to quasi-isometry, you cannot tell the difference. And the delta hyperbolicity is a finer state, is a finer property, but it's also quasi-isometrically invariant. In fact, maybe, yeah, in a second, maybe if you state the Milnor-Schwarz theorem, you will see one possible way of proving it. So, in fact, in general, we have the following. So you can recall that a group action of G on X is properly discontinuous if, well, for every X in X, there exists some U open set containing X such that the number of G in G such that GU intersect U is finite. And a group action is co-compact if, well, if the quotient X mod G is compact. Otherwise, saying there is a compact set, there's a compact set K in X compact such that X is the union of all the translates of G. Okay. So, in fact, so the important lemma here the Milnor-Schwarz lemma is that if the group G acts properly discontinuously and co-compactly, if G acts properly discontinuously and co-compactly on, again, a geodesic metric space, so this is important, otherwise it's not true. X. Yeah, and X is delta hyperbolic, then G, so yeah. So G is delta hyperbolic. Yeah. So what I want to say is that, yeah, it induces a match, the induced metric on X and the induced metric and the metric on G are quasi-isometric to each other, for instance, and X is delta hyperbolic. Then G is delta. Then G is word hyperbolic. So the point is G acts on some space in a properly discontinuous and co-compact fraction, then the metric on X and the metric on G are in the same quasi-isometry class. So one is delta hyperbolic if and only if the other one is delta hyperbolic. So as a corollary, well, you can see that, right? If G acts, if some Cayley graph is delta hyperbolic, then G acts also on the other Cayley graph in a co-compact and properly discontinuous fashion. So G, yeah, if Cayley graph of G for S is delta hyperbolic, then G is word hyperbolic. This is by definition. But then G acts also on the other Cayley graph in a properly discontinuous and co-compact. So the other one is also hyperbolic. So Cayley graph GS prime is also okay. So what are examples of hyperbolic groups? Well, clearly we looked at trees. So the easiest example of word hyperbolic groups well, you have G the free group in any number of element, in any number of any rank, because again the Cayley graph of the free group in R generators with respect to the standard generating set is a tree. And yeah, as we saw, is a tree of 2R, yeah, 2R regular tree. So clearly, if you pick another generator, so you get a different geometry, but it's still that. The other case, which we care a lot about, is if G is group of is a subgroup of the group of isometries of n-dimensional hyperbolic space, and so that again this action is properly discontinuous and co-compact. And so then we take M is the quotient of Hn by this action is a compact hyperbolic and manifold. So the classical case here is surface, a closed surface. So here, so as an example, we say the pi1 of SG, where G is a closed surface of genus G. Sorry, with SG is closed surface of genus G. And so this one has an easy sort of, well, at least for certain generating set, you can really draw the picture. So this is a classical picture. So the classical picture is you can think of a disk and you can draw a polygon in the disk, a regular polygon. So you draw a regular 2m gon or even 4m gon in the disk, right? Regular with respect to the hyperbolic metric. For instance, the easiest one is you draw an octagon. That doesn't look very regular. But and okay, so for instance, an octagon, and we make sure that the sum of all the angles is 2 pi, so that you see you in hyperbolic plane you have a whole family of regular polygons that you can draw given a number of sides, because you see you can make it sort of smaller, then it becomes more flat, so to speak, or you can make it much bigger and then it becomes more curved like that. This is the limit. This is the limiting behavior that you can do. And you see in the limiting behavior, the angle here is 0. While in the other limiting behavior, the angle is like for the Euclidean polygons, right? So whatever the Euclidean polygons angles are, well, in the middle, yeah. So we know that for instance, right, for octagon, for instance, example, yeah, if we want a more concrete example, we can say for m equals 2, so you take a regular octagon. Well, in the Euclidean plane, every angle of the octagon is 135 degrees, I think. So in the Euclidean plane, every angle is 135 degrees. So it's theta is 3/4 of pi, I think. All right, I think so. Yeah. So the total angle, is 3/4 times 8, so it's 6 pi. Right? While so we can choose an intermediate. So you see that. So in the limiton case here, the total angle is, so each angle is 3/4 pi. So we want to choose the intermediate, choose theta. You want them so that the total angle is 2 pi. So it can be done, because in the extreme case you get 0, and in the other extreme case you get 6 pi. So at some point you will find some position where this angle theta is 2 pi over 8. Right. So we start from here. In the middle there is some situation where 8. So a regular angle 4m gon where with internal angles theta is 2 pi over 4m. So such situation exists. And in that case, we can construct this quotient. So in that case, you have a picture which is somewhat intermediate, somewhat like that. Like that. And then we can label the sides in the following way. So we label the sides alternating, like, okay, this is A1. Next one we label it B1. The next we label A1 inverse. The last, then we label it B1 inverse. So each vertible of them, we label it like that, and then we see, yeah, we do this m times. So the next one is A2. This is A2 inverse. This is B2. This is B2 inverse. And so we label the sides. Label sides as A1, B1, A1 inverse, B1 inverse, and then we repeat this n times. So then we change the index, A2, B2, A2 inverse, B2 inverse, and so forth, up to AM, BM, AM inverse, BM inverse. And so we produce, so recall that the group of isometries of the disk, say orientation preserving isometries of the disk, is PSL2R. So we can find some matrices, some that map, yeah, this side to that side, basically. So we can find, so we assume that the sides where there is no inverse have counterclockwise orientation. So this side has this orientation. This side has inverse, so it has the opposite orientation. So there is a map. There is a matrix that maps this side to this one. So there is a matrix M(A1). So for each label, AI, find a matrix in PSL2R such that, yeah, MAI labels the side AI to A inverse. So these are the sides, in that sense. So it identifies the sides with the correct orientation. So you need ones for the HAIs and also for BI. So you do BI, BI inverse, and so forth. And so what it turns out is, since the angles are correct, the group generated by this matrix is discrete. So this is not completely trivial. This is the old theorem of Poincaré. So since the sum of the internal angles is 2 pi by Poincaré's theorem, it's a bit more general, but particular. Well, it basically says that if you have to check these angles and the sums over different orbits have to be rational multiples of pi. So in particular, if it's 2 pi, that's fine. The Poincare are the group which is generated by this. So the group gamma, which is generated by this matrix, is MI and BI. Is discrete in PSL2R. And in fact, so it acts and so it acts properly discontinuously and co-compactly on H2 or on D. So the picture is like that. The picture is like that. So you have a circle. And then you have this octagon. And if you apply those transformations, you produce other copies of the same octagon. So for instance, from here, if you map it that way, you will produce another octagon like that. And so forth. So it turns out, yeah, it turns out that if you do the identification, for instance, okay, we can test this bit, which you might have seen before, the topology course, right? So if you identify those, so this is A1 inverse, B1 inverse. So first of all, we can test that every vertex is in the same class if you do this identification. So if you think about, so if you take this guy, for instance, where is this identified to? Well, this is the head of A1. So the head of A1 is also here. But this is also the head of B1, right? So the head of B1 is also here. But then this is also the tail of A1. So the tail of A1 is also here. And now you can do the other one, A2 inverse, B2 inverse. And so you see that this is also the tail of B2, so it's the same as this one, which is also the head of A2, so it's the same as this one, which is also the head of B2, so it's the same as this one, which is also the tail of A2, so it's the same as this one. So in the end, by these identifications, there's only one class of vertices, which makes sense because by the Euler characteristic formula, you would have to have that, otherwise you don't have a correct surface, right? So let's double check that. So, but in general, right? So here, in fact, if we pick for M, so in this case, so note that all vertices of the polygon are in the same gamma orbit. And in fact, we can consider the characteristic function. So what is the quotient, right? So we have D mod gamma. Well, this is compact, clearly, because, well, it has a compact fundamental domain. So you see, you can pick K to be this original polygon, which is compact. So the quotient is a quotient of this polygon, so it's compact. And well, in fact, you can compute the characteristic, Euler characteristic of this, right? What is the Euler characteristic? Right, so this one you can think of this as a cell complex, right? So how do you compute the Euler characteristics, right? You take the number of one cells or zero cells, sorry, minus the number of one cells plus the number of two cells. And so what are the number of zero cells here in the quotient? 1, because all the vertices are identified. So the number is 1. And how many are the one cells? So, well, the one cells are the sides. So we have 4m sides, while we identify them in pairs, right? So we have 2m. And then we have a number of two cells. Well, how many two cells do we have? Two cells, a disk. So yeah, we have a disk, which is this one, right? This is 1. So just to check, the Euler characteristic is 2 minus 2m. And so the quotient is the surface. And what's the genus? Well, you know that the Euler characteristic of the surface of genus 2 is 2 minus 2g. So the genus G equals M. So in particular, if we start with an octagon and we do this identification, well, the quotient is famous surface of genus 2. Then if you start with a 12gon, you get surface of genus 3 and so on. And from the so that's just from a purely combinatorial point of view, but from the point of view of hyperbolic geometry, well, again, you have tessellations, and here you see at each thing, at each edge, you have a tessellation. It's hard to draw, and yeah, there's 8 of them actually here. The total angle here. So it turns out that since all the vertices are in the same class, at each vertex here, if you go around, you see these octagons, and you see precisely 8 of them. And that's why we had to pick 2 pi over 8. Each angle is 2 pi over 8. So when we pick, we have 8 of them. So we get angle 2 pi. So that's why we have a nice smooth manifold. So each angle is 2 pi over 8. And so you have 8 of them. So since we picked internal angles, theta equals 2 pi over 4m. This is true in general. Then at each vertex, in the quotient, we have a total angle of, yeah, that's right, of 4m times 2 pi over 4m. So 2 pi. And so in principle, this quotient might not be a nice manifold at this point, because you don't, this depends a little bit on this quotient. Because each point inside is not a problem, because we already have a neighborhood here. And at each point in here, well, we have that this is paired with some other side. So we have 8, half, so we have pi on this side and pi on that side. So that's also fine. The trickiest points are the vertices, but that's why we pick them like this. So the quotient which is SG, which is D over gamma, is a smooth manifold. Smooth surface. Okay, so this is a very nice geometry. It's a, well, of course, very classical, but it's a non-trivial example of a group which has a co-compact, properly discontinuous action on a hyperbolic space. And the group in question is the group generated by this, which is the same as the pi1 of the quotient surface. And so, in fact, this group, we know a presentation for this group. So for each genus at least 2, well, we know that gamma G is the group indeed generated by these AIs and BIs, such that 1 is less than I less than M. And also we have one, this is not a free group, we have one identification, which is given precisely by running around the boundary of the polygon and reading the labels. And all, if you basically, if you do the loop, if you concatenate all these paths, you get a loop. And this loop is homotopically trivial, so it can be contracted to point. So it's the, you know, it's the identity element in the group. And so the only, in fact, the only non-trivial relation we have is exactly that, this one. So usually it's written like this, that the product of the commutators is 1, is the identity. Right. So where recall the notation for commutator is AB A inverse B inverse. So this is a nice surface group. So again, gamma G is the pi1 of the surface of genus G, which is also can be thought of the disk quotiented by gamma G, through this representation of gamma G in PSL2R that I defined before. Right. So here, clearly, on this side, we have just the topological picture. You can start with just the surface as a topological object, and you have the pi1, so the space of loops of the homotopy. On the other hand, this surface also has a metric structure. It's an actual quotient of the disk, which has a nice hyperbolic metric by some discrete group of isometries. And so this surface, so again, SG equals D mod gamma G has a metric, as a hyperbolic metric of constant negative curvature, has a metric of constant curvature -1. Precisely because we start with the disk that has this nice metric, and the group PSL2R is a group of isometry, so it preserves the metric. So the metric descends to the quotient. So this is not just a manifold, but it's smooth manifold, and not just a smooth manifold, but metric Riemannian manifold, and not just Riemannian manifold, but hyperbolic manifold with a constant negative curvature. So again, all this, yeah, somehow this is not the topic of this course, but this is a very, very important example to keep in mind. Okay, so this is one example of a non-trivial example, non-free hyperbolic group. So in general, in higher dimensions, for any n bigger than 2, Well, you can consider again a group gamma, a group of isometries of Hn, again acting properly discontinuously and co-compactly. Well, if you just do that, the question need not be manifold, but it's an orbifold. So then, yeah, then gamma is word hyperbolic and gamma is isomorphic to the pi1 of the quotient. And okay, if we just assume the properly discontinuously and co-compactly, the quotient need not be a manifold, it could be an orbifold. But okay. So this is a hyperbolic orbifold. Okay, so yeah, also let me finish by saying the following. So, however, note that not all groups, fundamental groups of hyperbolic manifolds are word hyperbolic. So there are, so there are, you can consider, if you consider, Funk considers a discrete but not co-compact subgroup gamma in the isometry group, then gamma may not be word hyperbolic. So in fact, so in dimension 2 is kind of a slightly exceptional case. But in higher dimension, it's more tricky. So in fact, in dimension 2, well, it's still hyperbolic for some somewhat simple reason. So you can consider maybe someone's favorite group of hyperbolic of matrices, 2 by 2 matrices. If you take gamma to be PSL2Z as a subgroup of PSL2R, well, this is discrete, but not co-compact. And in fact, the fundamental domain is not compact. What's the fundamental domain of PSL2Z? This you might have seen in other courses. So if I look at the upper half plane, right? Yeah, exactly. So PSL2Z is generated by these two maps. Z goes to Z plus 1, and Z goes to minus 1 over Z. And so a way to find fundamental domain is the following. You write the unit circle. You draw the lines at 1/2, like that. And so you consider the following region. This is 1/2. This is minus 1/2. And yeah, it turns out, so if we call T of Z equals Z plus 1, and S of Z equals minus 1 over Z, well, this region is a fundamental domain. And what it turns out is that this side gets mapped to this side by t. It just translates by 1. But then S is a different type of element, S as a fixed point. So S of I is I. So this element, this point I is fixed. And what happens is that, this side is mapped to the other side. So this side is mapped to the other side like that. It's flipped like that. Okay, and so you induce a surface, quotient surface, but this quotient surface is 3 strange points. So there is omega. Let's call this omega, the third root of unity. And okay, this is the this is what is it? Omega square. 6 roots of, let's say six roots of unity. This is omega squared, but those are identified. So it turns out that the way you think about this is the following. So first of all, in hyperbolic metric, recall that the hyperbolic metric is the Euclidean metric divided by y. So if you go up, the distance between these two sides gets really, really close to 0. So this is not the picture is more like this. So it's more like these two sides go like that. And then you have this geodesic in the middle, like that. And this point is problematic, well, in the sense that you're taking if you think of it as made of piece of paper, it's like you're taking this piece of paper and you're folding it like that. So the total angle here is pi, it's not 2 pi. So this is slightly problematic. And on this point, well, what is the total angle at that point? Well, this point is identified with this point. So the total angle here is 60 degrees. And there's other 60 degrees on the other side. So the total angle at this point is 120 degrees. So this total angle is pi over 3. And the total angle here is pi. Right? The pi over 3, yeah, right? Yeah. No, pi over, sorry, 160 is what? Is 2 pi over 3. Yeah, that's 120 is 2 pi over 3. Yes. Okay, that makes more sense. Because pi is, you can think of pi as 2 pi over 2. Yeah, exactly. And so how do you construct the quotient? Well, one way to say is you can cut here and fold there. Right? You have this half, and you have this other half, which is sort of the back side, and you fold them. So in the end, you get a surface that looks like this. Because you see, yeah, if you think of this as having a front side and a back side, right? So this point is a point where the total angle is not 2 pi, but it's just pi, right? So this has angle 2 pi over 2, and this point has angle 2 pi over 3. So these are called orbifold points. That's why, because the total angle in this nice metric structure, yeah, it's not 2 pi. So on the other hand, this point up there, well, you see the surface is not compact. Because so this point, yeah, you see this short curve that you start with, the curve here gets shorter and shorter as you go to there. So this is called a cusp point. So in this case, so if you consider sigma, which is H2 mod PSL2Z, which is called the modular surface. This one is not compact, but it has finite area, finite volume. So the fact that it has finite area has to do with the fact that this goes up to, this grows like 1 over y. So yeah, you have to do the integral. It's not that complicated, but you have to do the integral. And so this is an example of a non-compact finite volume hyperbolic, well, orbifold, because it's not quite the surface, because it has these 2 problematic points. However, you can also find there is a group gamma, yeah, let's call it gamma 2 inside PSL2Z with finite index subgroup, such that in fact sigma 2, which is H2 mod gamma 2, is a surface, is a Riemannian surface. So basically, the idea is you can consider a slightly larger hyperbolic, slightly larger fundamental domain instead of that domain. You can consider the following domain: -1, +1, like that. You can consider this domain. And in fact, in this case, I think you just say, you just consider gamma 2 generated by the following: z goes to z plus 2, and z goes to -1 over z. And in that case, the fundamental domain is that. And let's see, it turns out that no, not this one, sorry. This one. So yeah, I forgot what is the correct generator. So definitely T. That goes, so there is one that maps this side to this side. So this map is clearly, yeah. This map is clearly z goes to z plus 2. And then there is another one. Okay, we have to think about, I forgot what the formula is, but you can find an element that maps this guy to this guy. We have to think slightly about it to see which one is it. But the point is then the quotient is a triply punctured sphere. So quotient looks like that. Yeah, it could be just a reflection at around 0, but no, but that's not in PSL2R. It has to be orientation preserving. Yeah. Yeah, I think, yeah, maybe you have to put this, yeah, maybe it's like, yeah, you have to put this one on the other side. So, yeah, well, okay, we can come up with a formula, but yeah. So anyways, so this group is not very far from this one. There is just a finite index subgroup. So this is a finite index subgroup of this one. And then when you quotient, you get again a non-compact And in this case, hyperbolic surface. Riemann surface, which has three cusps, with three cusps. Because, yeah, there is a point at 0, point at 1, point at infinity. They're all in different classes with respect to this group action. So what is kind of strange here is, however, in dimension 2, yes, you can construct a non-compact surface, but then what is kind of strange is, well, strange. It's a coincidence that this group still is hyperbolic in the sense of Gromov, because this group is free. So then it turns out that gamma 2 is isomorphic to the group, the free group in two generators. So it is still well hyperbolic, even though it does not act co-compactly on H2. And this is because in dimension 2, there are not really too many things that can go wrong. So now what happens in dimension 3? Well, in dimension 3, things can go wrong in a much worse setting. So for n equals 3, on the other hand, if gamma acts on H3, even orientation preserving, like discretely, so let's say properly discontinuously, and the quotient has finite volume, well, it is not the case. It is not necessarily the case, usually mostly not the case that gamma is word hyperbolic. And the reason is, well, it's harder to come up with a concrete group of matrices. I mean, you can, but like, so the reason is that if you pick G in the isometry group, yeah, let's say that if consider parabolic subgroup, so consider P the stabilizer of a point psi in gamma for psi in the boundary of H3, then P may contain copy of Z2. So the idea is the following. So if we pick, so this is a picture of, so this is H3, the upper half space, and this is the boundary of H3. We put it like in the plane. Well, you can pick a point psi in the boundary, and well, it turns out that, yeah, you can most of the time, if what you have is that the set of elements that fixes the psi fixes a parabola like that. And basically the situation is that this horrible is homeomorphic to R2. It's a two-dimensional surface. And so there are group elements that, yeah, you can move in two directions. So basically, you can yeah, I guess even the even easier case is if you fix the point at infinity, if you put, yeah, maybe the easier case is if you put the point x at infinity, so we put it up there, well, you can move in two different directions and still preserving the point at infinity. Right? So the fundamental domain is some sort of chimney like that. So basically you can easily construct a group where you put two different translations, and those would fix the point at infinity, and then you can put some other stuff in there, and the cusp, yeah, will have rank 2. Yeah. So the point is, example, yeah. Yeah, in this model, right? If you say H3 is x, y, z, such that z is bigger than 0, we can pick g of x, y, z equals, I don't know, x plus 1, y, z. So this is g1, g2, x, y, z is x, y plus 1, z. Then the group generated by g1 and g2, of course, is z2. And there is a way you can add some more elements, few more elements in the group of isometries, such that there's the gamma generated by g1, g2, gm acts properly discontinuously. On H3, and the quotient has finite covolume. That's finite volume. So this is an example of a group that acts properly discontinuously on a hyperbolic space. And in fact, even the volume is finite, the volume of the quotient, but the quotient is not compact. The quotient looks like hyperbolic 3-manifold. So there could be some topology here and here. This looks like a chimney like that. Like it has a square base, and yeah, it looks like a square times a half line. So there's a cusp. So this looks like 0, 1 squared times 0 infinite. Okay, good. Are there any questions? This is all the geometric part, which is somehow sort of just to remind you what are some geometric applications of what we're doing. So we can take a break before we start with the run and walk part. So we can start at 11:25. No, that's right. Okay, so I guess we can restart. So I think we have seen enough geometry for today. So let's start with now let's start with actual yeah, we're going more to the random walk plot. Okay, so first of all, okay, one other thing we have to say is we have to talk about isometries of hyperbolic spaces. And so again, if XD is a hyperbolic space, hyperbolic metric space, well, first of all, we need to give a few more definitions. So first of all, we say that a metric space is proper if closed balls are compact. So if for any X is a space, any R, the space of X in X, such that the distance between, sorry, Y in X, the distance between X and Y is less or equal to R, it's compact. So we looked at so far proper spaces, like example will be finite dimensional manifold. But then there's also interesting non-proper spaces. So non-proper example. Well, for instance, you would have a tree with countable valence. So tree with countable valence, meaning that at every point, at every node of the tree, there are countably many edges coming out of it. That's a perfectly good delta hyperbolic space, is delta hyperbolic. But non-proper. So that's the problem. Well, that's one of the issues, that in fact, in several cases where the group does not act on a proper hyperbolic space, but sometimes it acts on a non-proper hyperbolic space. So that's one thing. Right. Yeah. Okay. So now the other thing is for isometries. So okay. So given G in a group of isometries of this XD, we consider the translation length. Which we denote as tau of G. And this is the limit as n goes infinity of the distance between O and G and O divided by n. Again, the limit exists by subadditivity. O is some for some O in X. And once you look at that, then we look at the classification. So yeah, so classification of isometries of delta hyperbolic spaces. Did like classification of elements in PSTL2R. So this is generalization. So the first one is tau G is elliptic well, if it has a fixed point, okay, has a fixed point in X. So the classical example we know already is, G of Z equals -1 over Z if x is h2. So we know that the fix, so this would be a rotation at I. So this is, so in general, the classical case would be you fix a point and you're rotating around it. So but this could be slightly different. There could be more things happening here because there's more space. So you can fix a point and you can permute things near x, but that's still fine. Okay. So the other one is G does not have, yeah, so I guess there's two ways to say about it. Does not have a fixed point. In x, and tau of G is 0. So this case is the murkiest one. So you can sort of sweep a few things under the rug here, because in the classical case, the parabolic case, so G of Z equals Z plus 1, for instance, if x. So in this case, this point has a fixed point on the boundary, right? G fixes point on the boundary of x. And well, you can check the tau is 0 because if you go around, if you translate, yeah, the hyperbolic distance is sublinear, in fact, right? I mean, this is a classical picture that if you pick a point here and you translate it like that by n times, then in fact the distance, the hyperbolic distance, because the hyperbolic geodesic is like that, so the hyperbolic distance is actually log n. So that's why the translation length is 0. Even if you're moving n times, but there's actually the shortcut. So in fact tau is tau. However, in a non-proper space, there are various things that could happen. So it's not completely true that we have a very, very good classification of this case. But in any case, the other cases we have that if tau of G is positive. In this case, we call it G is called the loxodromic. And if so, G fixes 2 points. On the boundary of x. So in that case, it's actually much, this also behaves nicely, this case, because basically what happens is that there's 2 points that are fixed, psi plus and psi minus. And so basically it's, in the classical case, G would have to fix a geodesic between them. Well, this is not quite true in general, but still G coarsely does the same. G will translate along this quasi geodesic, and then it will, on the boundary, the action will be that G is repelling from this point and is attracting from this point. So one repelling and one attracting. So the classical case here would be, as I said, G of Z equals 2Z on H. So this should go 0 will repel, 0 would be repelling, and infinity would be attracting. Okay, so why would we care about this? Well, we have to give a definition, which is the non-elementary subgroup. So definition is a semigroup, even classification of semigroups is also even a bit trickier. But a semigroup gamma of the group of isometries is called non-elementary in this situation if it contains two loxodromic elements with disjoint fixed sets. So basically, in the picture, you would have 4 points on the boundary. And you would have an element G that fixes these 2 points and is loxodromic, and an element H which fixes these 2 points. And these 4 points are distinct. Okay. So we need at least that to be true for our semigroup for the random walk to have good properties. And so we define, so a measure as a probability measure on G, which is a subgroup of a isometry group of XD, is non-elementary well if the semigroup generated by the support of mu is non-elementary, as you could guess. Okay, so now we can state the main theorem. So Mar and myself, the following. So okay, well, well, in fact, this assumption is not really needed, but yeah. So we say that X is separable. Is separable if it contains a dense countable set. So okay, so let G be a group of isometries a countable group of isometries of a separable delta hyperbolic metric space. Okay. So, okay, we start, so we take our base point and let mu be a non-elementary measure on G. Then what? Then, first of all, there is the convergence property. So what is the convergence property? For almost every random walk Wn sample path, the limit of the walk exists. So, okay, yeah, I guess I haven't told you precisely yet what is the boundary. So a Gromov hyperbolic space has a natural notion of boundary. So, which I will tell you next. And in fact, this in this metric context, almost every sample path also converges to the boundary. So exactly like we did for the hyperbolic H2. So the other one is, well, you also have something like positive drift. So if there's no finite first moment, you cannot say that the drift is finite. So there exists L positive such that the limit over n of d o w n o over n is at least L for almost every omega. So at least, so the random walk does escape. Well, the existence of the drift, the limit, is more or less equivalent to the finite first moment. So if you have a finite first moment, so if mu has finite first moment, then, well, then indeed the limit exists. Almost sure. Okay. So this is the second statement, which is again generalization in many ways of Furstenberg's results for matrix groups, because in this metric context, indeed you do have the convergence to the boundary. You also have the positive drift. So yeah, and so what about the Poisson boundary? So for the Poisson boundary, of course, what you would like to have is that, okay, we have nu, which is the hidden measure of, again, of this W of this random walk on this Gromov boundary. And it turns out that this Gromov boundary is a metrizable space, and it's compact if the space is proper, but otherwise it's not non-compact. But still, you can think of that as a G mu space. So you can still think of whether this is the Poisson boundary. Okay. And so to do that, well, we need some condition, because yeah, so we need a properness condition. We need a properness condition to state, to conclude that this one is the Poisson boundary. And in fact, there's two properness conditions. So in the paper with Joseph, we had the weaker version of it, and actually more recently we have a stronger version. So maybe I can just tell you the stronger version. Why not? Right. So So the weakest version is the WPD condition. So WPD stands for weakly properly discontinuous. So we talked about proper discontinuous actions. So yeah, but in general, to ask that a group has a proper discontinuous action, that's too strong, but also it's too strong if you're acting on this non-proper spaces. Like if you're acting on this group, the space with this tree with infinite valence, then this is too much else. But WPD, which is I think is due to Basvina Fujiwara, is the correct, or at least one correct way to analyze this notion. So in general, we can define the joint force stabilizer. So the stub K, the stub K of X is the course stabilizer is a set of G in G such that the distance between O and GO is less than K. This is called a course stabilizer. And what is a WPD element? So define an element. It has to be a loxodromic element. A loxodromic G in the group of isometries of XD is WPD if the following is true. So you look at this group of elements that coarsely stabilizes elements on the axis of G. So the element is like that. So remember that if G is loxodromic, then take a point, you look at Gn of O. So G moves along, say, quasi-geodesic like that. And the question is, can it fix both can it fix both O and G and O at the same time? How many are there elements that can coarsely fix this and coarsely fix that? So recall that if the action is properly discontinuous, then the coarse stabilizer is finite. So now recall that the properly discontinuous implies that the stabilizer of K X is finite for every X and K. Right. So here, so here we don't want that. That's too strong. But we want to say, okay, so suppose there is an element that moves O not too much, and it also moves GO not too much, or GNO. Is it possible? And WPD tells you that, well, this is only possible for finitely many cases. So if there exists some O and some N such that the coarse stabilizer and the coarse stabilizer of O and the coarse stabilizer of H of G and O is finite. And there is on K, there is an assumption on K, any K, exactly. So if the correct statement is for any O in X and any K, constant, which is this ball, okay, is the size of that ball. Yeah, there exists some n such that this is fine. So again, it is possible to rotate around O somehow. This is allowed. But if you take 2 points which are far enough on this axis, so this is the axis of G, this is G plus geodesic, it's not possible to both fix this point and this point. So that would correspond to sort of rotate around this geodesic. And this is possible, but for only finitely many choices of H. Okay, so this is a fairly weak condition. And yeah, but we need some condition, because otherwise the action of G on X could be really bad. It could have like discrete, it could have dense orbit, and then we really don't know what to say. Yes? This condition is... No, this condition is interesting in non-proper spaces.
Oh, I see.
Yeah.
So you're not...
No, absolutely not. Absolutely not. Yeah. Yeah, exactly. This condition is useful in non-proper spaces. Yeah, exactly. Yeah. So we.
This
No, that's right. So there is a notion of there is WPD, and there's another notion which is called acylindrical. Yeah. So acylindrical is stronger than WPD. So in fact, historically, we first proved it for acylindrical in the original paper with Joseph, and then more recently we upgrade to WPD. But for certain actions, we don't know acylindrical, so we know WPD. So examples. Okay, let me just briefly say. So if G is the mapping class group, then we can take X to be the curve complex of graph. Then the action of G on X is acylindrical by Bowditch.
What is that?
Yeah, I can tell you what that is. Yeah. So acylindrical means that for any X and Y, the core stabilizer of X intersect the core stabilizer of Y. It's fine. Okay, maybe it's epsilon stronger than that, but this is the basic idea that you can take any 2 points, and now you want to say, okay, if I stabilize both one point and the other point, then this can only happen with finitely many choices. Yeah, let's say that the distance between X and Y has to be large enough. So this is stronger because we have to check every pair of points. Well, this one we don't. We just say, okay, we pick O, and we pick another point which is on the axis of G. So it's only in this axis direction that you have this property.
Oh, so this is all one specific.
Yeah, this is of one specific element. That's right. Right. So yeah, so this is acylindrical, and in fact, every Pseudo-Nosov element is WPD. But yeah, on the other hand, if G is out of N, for instance, and X is, for instance, I guess, prefractal complex, whatever complex, I think. So I don't think we don't know that the action is acylindrical, and maybe likely it's not. So not likely to be acylindrical. Cylindrical, but there are WPD elements. So in fact, the most recent paper has the following very general statement. So let me say it. So the theorem, the most general version with Barong and Kunal and Joshua. So it's Chala, Fresh, Farhani, Fresh, and myself. Now this is just last year. Is it like this? So suppose again, G is a group of isometries of delta hyperbolic space. Suppose that G is generated by the support of mu. Just, this might be movable, but anyways, let's assume that. And G is non-elementary. The action of G of X is non-elementary. And also it contains a WPD element. And contains a WPD element. Yeah, and moreover, and suppose that the entropy H of mu is finite. So we don't have any logarithmic moment here, even though this was in the classical setting, we had to, but in this new setting, we no longer have that. So as long as the entropy is finite, then this boundary of X with the hidden measure is a model, is the Poisson boundary. Oh. So you see that we do need certain level of openness, but somehow just the minimum, the minimum one. So of course, the applications of this are really general. So because again, so okay, the easiest one would be G word hyperbolic when X is a Cayley graph. Yeah, this action is proper, co-compact. So okay, this was, even though removing the just having the finite entropy condition was not known before. So even for just a word hyperbolic group acting on itself, we used to need some moment condition. Now there's no moment condition. But then, also what are the other examples? So again, if G acts on say Hn, for instance, so G is a fundamental group of a manifold. So this acts properly discontinuously, for instance. There is no need to be co-compact. Then again, we can take X equals Hn. So we say that the Gromov boundary of Hn, which is just a geometric boundary, is the model for the Poisson boundary. So this covers all the hyperbolic manifolds. There's interesting other examples. So G is the free group of countably many generators acting on itself. So X acting on its Cayley graph. This is a infinitely generated group. So the Cayley graph is an infinite graph. It's an infinite tree. But the action turns out to be WPD. This is a nice exercise actually. Yeah, and then the other groups that you care about maybe in geometry or so if G is relatively hyperbolic, let me just say these things. And X is the cone of space. another example. So in this case, it's similar to this group acting with the cusp on HN, but it's more general. But then you can act on a non-proper. So this space is already non-proper. So you need a non-proper theory to do that. And then again, these groups that I was just mentioning before. So let me just write them. So you have G, the mapping class group acting on the curve complex. G is out of N, acting on refactor complex. G is a right angle arching group acting on the extension graph, for instance. So in this case, the action is acylindrical, I think. In this case, the action is acylindrical. In this case, the action is not acylindrical, but WPD. And then what else? Well, and yeah, if you care, the other group, it could be the Cremona group. There's the group of birational transformations of P2. Well, it's a group coming from algebraic geometry, and this acts on the so-called Picard bounding space. This is very, in a way, exotic from the point of view of geometric group theory, but still interesting example for algebraic geometers. It turns out that this space also is hyperbolic. In fact, it's very similar to infinite dimensional hyperbolic space of constant negative curvature. So it's similar to H infinity in many ways. So this is kind of just by chance it happens. It also works in this case. Yes.
Before you said like an action as WPD,
Mm-hmm.
you would say that like the whole group action is WPD if there exists a WPD element?
Yeah. That's what I meant in a loose terms. Yeah, exactly. Yeah. So yeah, I mean, the question in general, the question on which elements are WPD is a hard question. So usually what one can prove usually in these settings is that if there is one WPD element and you do this random walk, then random WPD elements are generic with respect to the random walk. So the probability of elements being WPD goes to 1. But on the other hand, for a precise element, sometimes depending on the action, for instance, actions for out of N, for instance, I think in that case, it's really not completely determined which elements are WPD, which elements are not. I mean, this is still an active area of research. Yeah. Okay, so I don't know. So at this point, I think probably not make much sense to start with any proof of anything because we're pretty late. So that's good. So anyways, so I'll start with some ideas of the proof on Thursday. So in a way, you will not need the geometry, to be honest, because it will just be about metric spaces. Okay, good. See you guys.